Bismillahirrahmanirrahim. So far we have just talked about discrete random variables or discrete distributions, probability distributions, like flipping of coin or throwing dice. But there are events which are continuous in nature, and now we will talk about continuous random variables in this video and the other videos. So our topic is continuous random variable. Continuous random variable, a continuous set of numbers, sometimes referred to as an interval, contains all the real numbers between two limits. For the limits x1 and x2, with x1 is less than x2, there are four different intervals distinguished by which of the limits are contained in the interval. So thus we have definitions and notations for the four continuous sets bounded by the lower limit x1 and upper limit x2. So we have got two limits, x1 is for lower limit and x2 is for upper limit. So if the limits are written like this, parenthesis x1 comma x2 parenthesis, is the open interval defined as all numbers between x1 and x2 but not including either x1 or x2. So here the numbers between all the real values between x1 and x2 are included but excluding x1 and x2. So formally it is written like this: x is given that x1 is less than x and x is less than x2, means the value of x is greater than x1 but less than x2, and excluding x1 and x2. And we have closed interval as well, where x1 comma x2 written in this square brackets is the closed interval defined as all numbers between x1 and x2 including x1 and x2. So formally we write it like this: bracket x1 comma x2 bracket is closed is equal to curly bracket x, given that x1 is less than and equal to or equal to x, and x is less than or equal to x2. So here the value between x1 and x2 include x1 and x2 as well. And if notation is written like this, then it simply means that it includes x1 but excludes x2, and this one says that x1 is excluding but x2 is including in the limit. So we just simply write the limits like this: x1 is less than equal to x and but less than x2, because x2 is not included. And here x is given x1 less than x, x1 is less than x and x is less than equal to x2. So if we ask what is the probability that exactly peak demand will occur, that electricity peak demand will occur at exactly 12.01, so I'm not going to read this whole number over up to here, 49 p.m. So of course here we are talking about very maybe micro or nano or maybe much lesser degree of precision of time in seconds. So the answer is 0 probability. The reason is it is virtually impossible for the peak load to occur at this split second in time, not a slightest bit earlier or later. Now if we ask what is the probability that electricity peak demand will occur at exactly 12.01, and I'm not going to read the whole number up to this 49 p.m. The answer is 0 probability. Reason is that it is virtually impossible for the peak load to occur at this split second in time, not a slightest bit earlier or later, because here we are talking very precise time. So when we are talking about real values, we cannot predict the value or future value exactly for that real value, because the real value itself goes to infinity. In discrete random variables, the flipping coin once, or getting head one or twice or thrice, this is possible. But when you talk about real values, then to know whether what's the probability for that event to occur at that very precise time, real value, is very difficult. So in that case, we say the answer is zero probability. A random variable, if it can assume any value in some interval of real numbers, and probability that it assumes any specific value is zero. As a result, a continuous probability distribution cannot be expressed in tabular form like discrete random variables. Instead, an equation is used to describe a continuous probability distribution. The equation used to describe a continuous probability distribution is called probability density function. What is probability density function? It describes a continuous probability distribution within an interval. So for example, what is the probability that event x will occur between an interval a and b is that we simply integrate it in the interval of a and b. This f of x is the probability density function, and this f of x is for this random variable x. It is impossible to define a probability mass function for a continuous random variable. So PMF is only for discrete random variables. For continuous random variables, we do not describe or define probability mass function. All probability density functions satisfy the following conditions. The random variable y is a function of x, that is y is equal to f of x. The value of y is greater than or equal to 0 for all values of x. The total area under the curve of the function is equal to 1. We will explain these things in coming slides. Now, example of continuous random variable. For example, measuring arrival time t, such as the arrival time of a particle or a customer or some other event, or maybe a packet. Measuring voltage V, such as the voltage across a resistor. So what will be the voltage? So we know that the voltage is analog value. So in that case, predicting exact value is not possible. So what we can say is that the voltage will be within this limit. It can be from we can try to determine whether it will be within that interval, but we cannot say it will be exactly this value will occur or not. We cannot predict that. Measuring the phase angle A of a sinusoidal radio wave. So these are the examples of continuous random variable. CDF of continuous random variable. The cumulative distribution function of random variable x is f of x. F of x is equal to probability x less than equal to x. Means the cumulative distribution function for any random variable x, denoted by f of x, is the probability that x assumes a value less than or equal to x. Graphs of all cumulative distribution functions start from left of 0 and end on the right. All CDFs are non-decreasing. The probability that the random variable is in an interval is the difference in the CDF evaluated at the ends of the interval. So in future slides we will see the examples which will help us to understand these properties of CDF. A probability density function is a function that covers an area representing the probability of realization of the underlying values. The area under PDF must be equal to 1. The PDF of a random variable synthesizes all the probabilities of realization of the events. So what this PDF gives us, it only calculates all the probabilities which of realization probabilities of realization of the events. So if what is the probability for that event to occur? So we just get that very probability, and that probability is predicted using PDF function. Different random variables have different distributions which imply different PDFs. Unlike probability mass functions, the output of a probability density function is not a probability value. To get the probability from a probability density function, we need to find the area under the curve. So this is what it means, I meant over here, that the total area under the curve of the function is equal to 1. So actually we are talking about this area. So this area is shown over here. So this is, for example, we have taken the this is it is representing a normal distribution, but here we will not talk about this normal or whatever it is, because we have not talked about it so far. So just assume that we are talking, this is a curve, and we are going to I need this just assume that this line is representing probabilities. So for example, if I want to know what is the probability that the outcome is between 0 and 1, so it is not just I will look at these values over here, or I will say that the probability of is like 0.4 to 0.25, because these are the values on this line. No, but I will find this area to get the probability. So the shaded area is the probability of the outcome being between 0 and 1. Hence we say that the integral of the probability density function between 0 and 1 is equal to the probability that the outcome of the random variable is between 0 and 1. So this integral between 0 and 1 of PDF is the same as gives us probability of x to occur between 0 and 1. To calculate the area under the curve, we use the cumulative distribution function, which calculates the area under the curve from negative infinity to a particular value. So area A of a rectangle is A is equal to W into H, width into height. So width is equal to W is equal to 1 minus x. In this example, we have taken this, say this is A, this is B. So A is equal to 1 and B is equal to 6. So actually it should be 6 minus 1. So W is equal to B minus A is equal to 6 minus 1. We know that the area must be equal to 1. So therefore 1 is equal to 6 minus 1 into H is equal to 5H, or H is equal to 1 by 5 is equal to 0.2. Hence, the PDF uniformly distributed RV can be represented as a graph shown below. So this is its height 0.2 and this is its width. The PDF is a complete probability model of a continuous random variable. While there are other functions that also provide complete models, the PDF is the most useful. One reason for this is that the graph of PDF provides a good indication of the likely values of observations. So let's have a look at this example. The figure depicts the PDF of a random variable x that describes the voltage at the receiver in a modem. So this PDF over here is actually describing the voltage at the receiver in a modem. What are probable values of x? Note that there are two places where the PDF has high values. Over here at -5 it has got the maximum value, and at 5 it has got the maximum value. So the PDF indicates that the random variable is likely to be near -5 and +5 volt. So -5 is for 0 and +5 is for 1. Values from far from ±5, away from either -5 or away from 5, are possible but much less likely, because here we have got the peak. So to have this value, the probability of having any value greater than 5 or any value between 0 and 5 or -2, -3 and so on is may occur in case of distortion, but much less likely. So the expected value of a continuous random variable is simply multiply x by this PDF function f of x, and then integrate it in the interval -∞ to infinity. That gives us the expected value a of x.